Okay. We're starting 5 minutes early because I think it's a good idea to let everyone settle in. Because this live stream wasn't scheduled quite as publicly, and that is due to the account that it kind of was a bit more abrupt, slightly. Yeah. But yes.
No, I'm not. Where can I find the stream? Am I crazy?
Hold on, I can.
Do I just not have the right?
Well, you're presenting.
Channels?
So, you know.
Yeah, I know, but I want to see chat.
Hold on, I can send it. I'm also sending it on the library.
I'm going insane.
At here. There we go.
Yep. Oh, it's Make It Community. I was on the main channel. I'm going insane.
Yeah, unfortunately, this isn't the main channel because I find that a bit. I know it's a paranoid thing, but I worry that it might be a bit misleading with the Make It channel. So I made a whole separate channel for everyone who, just to clarify, like, this isn't mine. This is other people.
Yeah, that's entirely fair. You know.
So hi there, Komi.
I'm literally right there.
Yeah.
What do you say?
Hi there, Komi. Hi Joel. Hi Poncho. Hi Panzer. Hello everyone. And this is a row. You can see the name in the middle of the screen. Their presentation, and I'm also going to link their paper for everyone to follow along. I would really recommend that, as we to just, well, first of all, look through the paper regardless, and then also have it open. I tried to put it in the description, but YouTube didn't let me because the channel wasn't verified enough. So
yeah, the presentation is not in the same order as the paper, and it goes over most of the same things. So read the paper afterwards. It's also more in detail than the presentation. And yep. Am I not a bit quiet?
I just enloudened you. I can enlouden you some more.
I have been enloudened.
Yes, I've been enloudened. I'm going to be, I imagine, quiet for most of it, unless I have questions, obviously, but I don't want to interrupt, so once the presentation begins, you can all adjust your sound appropriately. I can also make myself a bit more quiet right now. There we go.
Yes, I could see my volume bar increasing.
Yeah, I wasn't lying. I deliver.
No, but it's
Okay. I think we could be ready. What do you think?
Yes.
All right.
Well. Welcome everyone to this presentation, which is about my little paper, which is Theorist Toolbox, Analytical Mechanics. We're gonna start with a little introduction, then a segment, an interesting segment where you have to trust me a bit. We'll do all the setup for the things you had to trust me before afterwards retroactively, so we'll justify most of the things we see in the introduction afterwards. And then there's a bit of payoff. I think it's a lot of payoff, but I'm maybe biased because of the fields I like. In what I think will be interesting. Oh, I have a mad delay on the stream. Hold on. Up. Fixed it normally. Perfect. So why am I talking here? Who is this PNG guy? Well, this talk is about a paper that has the same title, so Theorist Toolbox Analytical Mechanics, it's the title of the stream, in the Make It library. This talk will not explain everything the paper explains, because there are some examples that are rather long, I think, and there are some parts of the exercises that are rather technical. So everything is explained elsewhere in the paper, and the exercises have a separate solution paper that you can go and check if you feel like this may be an insurmountable task, which it's sometimes look like. I feel I had to look up some of them myself. So, you know, it's not because I wrote it that I wrote it entirely without help. Why use analytical mechanics? Because picture this. You are a high schooler. You just learned about Newton's equation and you're like, I don't think I will need anything else ever in my life. You are wrong, but you do not know yet that you are wrong. So to show you how wrong you are, picture in your mind n pendulums. I think we should say pendula, by the way, because that's the correct way to say it in Latin, and pendulums just sounds weird in my mouth. It's fine with cactuses because it has normal form. Well, anyway, each one has a length r, and they're all connected at their ends, and they're all massless. So all the pendula don't have a mass, except at the end of the last one there is a mass m. I found this nice little picture on the internet that I edited to fit my specific scenario. Ignore the big ball here. They're just directly connected. This is just part of the pendulum. It shouldn't be a big ball. I even edited the massless in. But yes, once again, I also do like dendula. I have no idea what dendula is, but it's fine. Let's stay on topic. We'll have some starting assumptions. So first, L is going to be our Lagrangian. It's going to have the form kinetic energy minus potential energy. And so that's the first assumption. For objects, so not fields, so a beer bottle falling down, a water bottle falling down, a rocket going to space, stuff like that, the equations of motion are going to be the total derivative along time of the partial derivative along the total derivative of a coordinate is equal to the partial derivative along the coordinate. This may seem a bit weird, but it is fully justified. I will justify it all later, okay? Promise. And for fields, which are like electromagnetic, I think you can do the same with the gravitational field, but it's very different. Perhaps I'll explain this in some other paper or presentation. You have this equation, which may look completely barbaric to you if you're a very Latin person, but these are some extra alphabet letters. These are Greek letters. There are some conventions that I will use throughout, which is the Newton dot for the total time derivative. So A dot for anything is the total derivative along A, and if A depends on the coordinates, this means that you have to take the partial derivative along time, and then add to it this little nabla, and so this is the gradient, and this is the total derivative of the coordinates. The coordinates, interestingly, are only functions of time in this framework, in the framework where I use this notation, so it's fine. This is an actual total derivative, which is the same. Yes, and then there's the Einstein summation convention, which is I have heard that it's like the signal that this person does relativity or quantum mechanics, like QFT. That's the way they find out who we are. Where if you have this thing, it means that I'm summing over all space-time coordinates for this. So there's a big sum hidden there. And you have this thing, it's only space, there's no time. So this is like a dot product of vectors A and B. You have each AI, BI, or AT, AX, those are the coordinates, and you sum over them. It's kind of like matrix summation in a way. Imagine these are matrices if you want, but these are not. This is a vector and this is a one form. Anyway, describing the system. So this is the same as in Newtonian mechanics. We all start the same way. We have to find the coordinates. So our position vector is just the sum of all these vectors that each pendulum forms. Each one adds some part to the position. So you can just add them all. This is a vector addition. This is fine. And then you take the total derivative along time and you get speed, v. V for Vitesse, of course. And you get this formula, which is also very nice. I don't think there's a calculation mistake, but I sometimes get the signs messed up. So it's fine. Just assume the signs are correct if you see a mistake. I don't think there is one. I checked this like 3 times. Now that we have described our system, I will not contemplate the idea of finding the equations of motion for a Newton way, but you can try at home. It's absolutely horrendous. It's a nightmare. Instead, I will show to you that it's much simpler to do them in the Lagrangian way. It's still a bit complicated because this is a very complicated system and the equations at the end are very ugly and cannot be solved analytically. But we can always just find the equations of motion, and then someone who's actually interested in behavior can just put them in a big computer and it's all going to be fine. So we said assumption 1, the Lagrangian is the kinetic energy minus the potential energy. The potential energy only depends on the height of a thing, so it's only the y coordinate, and here you have it, minus cos theta, hold on, here. So this is a plus sign here. The two minus cancel out. You have the MGR prefactor, obviously. And here you have the squared speed. This is a dot product, by the way, in the squared. This is the dot square. So you can expand this dot square into this thing and use the bilinearity. Sorry for the French. Bilinearity of the scalar product to take out the sums, take out the theta dots, and have only this formula remaining. And this is just a difference of angles inside a cosinus. So we have this nice coupling term that will be very important in the next thing, and this gravity term. We can multiply at will by any non-zero factor, and so we multiply by 2r we multiply by 2 over r squared, I think, yes, to get this for a format formula with the omega squared. If you ever solve the simple pendulum, which is also quite difficult to solve analytically, if I'm correct, well, without small angular approximation anyway, it's the same omega. There's no difference. You should have recognized this also. Now, for the equations of motion, remember, we need to take the partial derivative. This is West's assumption too. We need to take the partial derivative along the coordinates and their derivatives. So just for clarification, this term is the cosine. I spelled out here what it gives in each form, but it's always the same because sine is an odd function. So all these are in fact different ways to state the same form, which you have here. And the second term, you only take the sum. You only take the one term in your sum that corresponds to the specific theta a that you are considering. The rest of the terms, check out. Because this is a double sum, you still have one sum and you have a 2 that comes out. You can see this if you take a scalar product of two vectors of 2 times the same vector, and hold on, this doesn't work. Anyway, there are ways to see it. If you take the scalar square of a vector, I think this it's quite easy to see that depending on the coordinate you're deriving along, you always have something of this form. But you only have one sum in this case, so I don't think this is quite the example to use. Imagine summing over all the terms of a matrix, but the matrix is symmetrical. This is basically what we're doing. This is also not a very helpful analogy, so I'll just continue. Then the derivative along theta dot is much easier to compute because there's only the kinetic term that has some theta dot. And just notice that we take the specific term where theta a is equal to, a is equal to I in this shape. And because we sum twice, we have to take the term where a is equal to I, but also the term where a is equal to j, and then I relabeled it into I is equal to j. It's very complicated just for this simple expression. Then I make all the 2's disappear because they appear everywhere. So you notice I forgot 1 over 2 here, but it's fine. It's fine. Nobody cares. You take the total derivative along time, and you have 2 terms. So one where we derive this, and the second term where we derive this term. And you can notice that this theta j, theta a also appears in the right-hand side. So we cancel it out. And we are left with this, the specific angle of motion for each equation of motion for each angle theta a. So we have n of these, which is already quite bad. And they're all coupled equations. And as you can see in each equation, the theta dot dot of each coordinate appears. So this is impossible to solve analytically, even for n equals 2. It is possible for n equals 1 because it's a simple pendulum equation, and I think you need to use I don't remember the name of I think it's not Becquerel, it's the other one. You need to use some functions that aren't really defined analytically. They're only defined in terms of like weird integrals. I don't quite remember. Anyway, this is very hard to solve analytically, so I'm not going to do it. You see that I didn't. Well, at some point I used a free body diagram, but that was only for illustration. I didn't compute each force on each pendulum and have to draw it out and have to spell out, oh, F equals ma at all these points, and then figure it out. Those are all tension forces. So those are all forces that you cannot really model in in any way because they always resist in the same way, or they always offer the resistance to the force that is opposite to them. So there's really no way of solving them easily, because then you have this big system of I think it would be n-1 or n coupled equations. This is basically impossible to solve in Newtonian mechanics. In analytical mechanics, I had the equations of motion rather quickly, and this is solvable. You can actually compute this. Well, solvable. This is computable. You can put this in a big computer and have what you wanted. Also, if you take big N equal to 1, you only have the 1 theta dot dot here, so the cosine becomes 1. There's only one term in this sum, and it's 0 because all angles are the same because there's only one angle. And this is this usual term. So you recover the simple pendulum if you take only one. So that's a nice sanity check. Another thing that you really cannot do in Newtonian mechanics, and that analytical mechanics has a big framework for, is waves propagating on a surface. So fields in general, like electromagnetic fields, are very, very studied using analytical mechanics. Without the Lagrangian framework, I don't think we could consider the fields as we consider them nowadays. And anyone who has done particle physics in their life will tell you that fields are, in fact, the only thing to really exist. So it is. Sadly, I did half of this presentation, well, more than half of this presentation for nothing, because I talk about things that aren't fields instead, that are really composites of fields. But it's fine. It's a useful approximation for most purposes. Here, we take the same sum here, so the Einstein convention, remember, our third assumption for the equation of motion. You take the derivative along the field. There's only one dependence that's directly on the field. All the others are on the derivatives. And you take this complicated looking thing, but basically because everything is a square, you can just like pop the square, and this is that almost direct. And since you derive once more afterwards, you get this equation, which, if you have done some waves, I think we see it in first year, but no, first year of undergrad. But I don't know if in America you see this as early as we do. So if you don't know, this is the equation for a wave with this specific phase speed. If you take no potential or constant potential. If you do something else, if you put a little potential here, it possibly becomes much more difficult to solve. I think you can make a Klein-Gordon equation out of this, which was one of the early models for electrons. But, let's not go into that. And also, why use analytical mechanics? Well, you need Hamiltonians for quantum physics, and I think there's a video on the Make It main channel where they explain how from Poisson brackets you want to commutators, and how the Hamiltonian gained its big role in quantum mechanics. All of modern theoretical physics is built on Lagrangians. You have the standard model that is a big Lagrangian. If you've not seen it yet, I encourage you to go. Because I'll be talking for some while, so just Alt Control Tab, go into another thing and type standard model Lagrangian and see the big thing with looks like how can I describe it? Those scrolls that you get in video games where they just put
just an ancient tablet of indescribable knowledge.
Yes, it looks like linear B basically, but very very dense, It's very interesting to, as you progress through physics studies, go, I recognize this term. Because usually the first term, you can find the first term in the paper, I think. Because usually the term they write first is the photon term. So it's the classic electromagnetic term. Yeah, very interesting. Also, the post-general relativity theories. So, theories that say, this is in fact just a first order approximation. Second order actually, but this is just like an approximation. We can do better, and try to add more terms and see what the coupling constants are before these terms. And it's very difficult because most of the time you just end up with nonsense, like you have gravitational waves that propagate retrocausally or stuff like that. And all of these are usually defined through Lagrangians. So if you one day want to do anything theoretical, you need to use Lagrangian. I say this, but this is mostly for fundamental physics. If you want to do fluid mechanics theory, I don't think Lagrangians are this important. If you want to do nonlinear physics, it's nice to know analytical mechanics. It's better, but there are some other methods that are way, way more important. So, it's not the end all be all of physics. Yeah, most people, well, most physicists, like experimental physicists, etc., I think they get by just fine most of the day, not seeing a Lagrangian each day as some other people do. But some people are really obsessed and do one Lagrangian per day. So, whatever floats your boat. You can, so we can start setting up what we wanted to find. And the first thing we will justify is our second assumption. The difficulty here is to introduce the first postulate of analytical mechanics. Historically, people at some point found out about Fermat's principle. So you'd assume Fermat found out about it, but I think it wasn't him, it was someone else. I don't know. I think I remember this, but well. Fermat's principle is that light always takes the shortest path between 2 points. And I don't remember quite the name of the guy. I think he was French. He was like, maybe we can try to generalize it. There's a Veritasum video about the historical context about this, by the way. Maybe we can try to generalize this. Let's say every object that moves tries to minimize their path, but they have different coefficients for their path, So like a ball that rolls on a hill, it can't just fly in a straight line because it isn't light. So it has to go on a different path, and we have to somehow constrain it such that the path it follows is the actual physical path. So he was like, we need to minimize the weights of the path that we take. And how do we measure the weight? Well, it's the Lagrangian integrated over the time it takes to travel. And he called this the action. So we want to minimize the action, which is the weight of the path. And for this, we can just perturb this action. So we Taylor expand, hold on. First, we put a little perturbation in the path we follow. So imagine a little delta x and a little delta x dot, which is this, I think delta x dot is the derivative of delta x. We don't consider these perturbations to be independent because they're not really independent. And you put a small perturbation, then you Taylor expand this, and because those are vector quantities, you Taylor expand using not just derivatives like you usually do with Taylor expansion, but these are gradients. This is the gradient. When I don't say anything about the gradient, it is about this normal spatial gradient. If I say something, it's that we use this other vector coordinate. So we get these two separate terms that add onto the main term. The main term is the external path. So it's what we want to minimize around. So the perturbation around it has to be 0. We don't consider higher order terms. Some people may be like, that's not very exact. But in fact, what I do is functionally equivalent to taking the functional derivative. So mathematizations. We integrate this second term by parts. We get the second line. And this integration by parts, so hold on. We derive this one, and we integrate this one. We say that there are no edge terms because we can just say that our perturbations to the main path just doesn't perturb the starting and the end point. Because, well, obviously it tries to go somewhere like it wouldn't work axiomatically if we could perturb the start and end point, trying to find a minimal path between the start and end point. So that's fine. And then we notice that this delta x dt term isn't common in two integrals. So we can just use the linearity of the integral to get this thing. And we want this to be 0 for every perturbation. So whatever the shape of this function, this has to be 0. The whole thing has to be 0. So this specific thing has to be 0. And so we find the Euler-Lagrange equation, which is this is equal to 0, which was our second assumption. So now that we have this, we can justify our first assumption. We have this Euler-Lagrange equation. I just reshaped it so that we don't have a weird equals 0 somewhere. And we have our Newtonian F equals ma, beloved by all. Oh, those were the days, right? We can write this in a more expanded form if we use m equals ma to, hold on. Ma is m dx dot over dt. So it would be x dot dot, but it's more clear if I do it like this. And we can see that if you pull out the d over dt, you get that mx dot is equal to the gradient along x dot of L, and the I recognize f equals ma and nothing else. Everything is f equals ma on this slide, so it's fine. It's just all restated in very different ways. So the gradient of L has to be f, and if something is the gradient of if the gradient of a scalar is a force. Oh yeah, I forgot to put a f in a vector form. It's fine. Everybody knows forces are vectors. This is the potential energy, right, for conservative forces. And here we know that the acceleration is we know that the right hand side has this form. So if you integrate this along x dot, you see that it's mx dot squared over 2. So that's the kinetic energy. So we have the shape we wanted. L equals t minus v, which is basically f equals ma, but restated. Yes. For fields, now we don't have this nice sanity check of f equals ma, but it's fine because we know that Lagrangian is t minus v. And so we can, for a field, we have this slight difficulty that the evolution along time depends on the shape of the field in general. There can be influences on this field that come from neighboring parts of the field. So we have to integrate not just over time, but also over space. So in the end, I will stop doing these double integral things and integrate over space-time because it's way easier for everyone, especially for me as I was writing this beamer. So we will have our Lagrangian here that depends on the fields and on the derivatives of the field. You can put higher derivatives there. It's an exercise in the paper. It's not very interesting physically. I don't think there's anything that obeys third order derivatives that is very physical or physically interesting. We do the same trick. We perturb this. So a Taylor expansion, we get the perturbation term. We get that it's this thing. Then we do the same thing. We integrate by parts. At the edges of time, there's no perturbation. So the perturbations vanish at the edges of time. And we can say that either our space is borderless, so we consider something like I'll summon the differential geometry people again, but we can either consider a compact borderless manifold, so something that's closed, or you consider something that is infinite, and so that doesn't have a border. I don't think... Do you say border in English for Bohr? Yes, you do. So we integrate by parts, and there's no little closed term. And we get the equations of motion for a field, which was our third assumption. So everything was justified. It's fine, you guys. No need to stress out. Now, there was a lot of setup. Let's try to get something else out of it. And for this, I want to introduce Noether's theorem. But hey, we will solve a problem without ever using the equations of motion, okay? So no Euler-Lagrange, no F equals ma, none of this. Just pure conserved quantities. We will derive the classic orbit of a planet around a star. So let's fix the star. We say the star is fixed at the center of our grid. And we choose spherical coordinates such that the planet is in the equatorial plane. We choose our coordinates so that the planet is always in the equatorial plane. We know this because its position is one vector that comes from the origin. Its velocity is another vector, so it defines a plane, and there's no physical way for it to get out of this plane because the force is purely radial, and so it has to stay in the same plane, but also its angular momentum is conserved. Its angular momentum are in this coordinate system. And we also have conservative forces, so energy is conserved. Let's write this all out. So this is the conservation of angular momentum. We'll note the reduced angular momentum J tilde. This is the reduced energy that I put a factor of 2 so that there's nothing annoying here. And we have this form for the energy. So notice here you have the kinetic term, here it's the potential term. And so we have directly the equation we want to use, which is that the energy, which we can find by the initial conditions, is equal to this formula. The angular momentum we can also find by the initial conditions. So this is a closed form for the trajectory. You can, I think this is what they use in orbital mechanics solvers. I think Kerbal uses something similar. Anyway. But we saw the power of conserved quantities. It was very quick, very easy. I just did a bit of algebra. The important part of algebra that the theta point thing can be eliminated using J. And we have this this very powerful thing, but in a general setting, this was easy. This was like very obvious that the energy was conserved and the angular momentum was conserved. It's a typical example for conserved quantities, right? But in general, it can be more difficult to find conserved quantities because the symmetries can be weirder or they can be less obvious. So in general, how do you find the symmetries of a vector, of a system? I thought about killing vectors for a second, but it perturbed me. This is what it should look like in the end. This is the conserved quantity according to Noether's theorem. So let's try and find it. If we have a continuous symmetry, we want the action to be invariant under this type of transformation. So T becomes T prime, Q becomes Q prime, and Q dot becomes Q dot prime. In an infinitesimal form, parameterized by this parameter epsilon, let's say we don't take the full transformation, we just take a little transformation. We have these small perturbations. So this amounts to taking a derivative. Again, this is a Taylor expansion. It's always the same trick in physics. And so we can inject this all in our form for the action. Recall, the action is the integral over time of the Lagrangian. We put everything in there, but it's quite bothersome because this t term in the L, we'd like it to be just t0, or just t. I'll drop the 0. So we do a change of variables, and it introduces this nasty-looking dependence into the Q perturbations. Also notice I don't really care about the parentheses in my integrals. The integral stops where the dt is. Everything else is a lie anyway. So yeah, be careful. So we have this, and then we can also Taylor expand this to get the perturbations out. And we just denote t prime, this thing. So this new t with a minus sign here will denote a t prime. And so we have this form for our action. So this is still S because all of this is invariant. And I'll be more rigorous in the field version with the big O notation for epsilon squared. But what I did is that I ignored everything that was a term in epsilon squared in the development, and I continue to ignore it for the rest of the presentation. So now we need to take the derivative along epsilon. Why? Because we know this is invariant. So the derivative along epsilon must always be 0. And to make all the things easier, we can just take epsilon to be 0. Black Thunder, I am also French, so please don't be careful at what you say in the chat. Okay, so we take epsilon to also be 0, and we get this form for it. So, well, we had this form for it, and we need to see what each term gets us in the derivative. So the border terms here, these two edge terms, they also are included in the integral, and they just give us the value of this as epsilon is equal to 0. So this gives us LTQ Q dot delta ST being the little transformation, the little nudge, well, more like the direction of the little nudge at T1 and T2. This is basically what we would have if we solved an integral that was some time derivative of this. This term, we already have an, hold on. We still have to think about this term. So the only important thing is that there is an epsilon dependence in these t primes, right? So each t prime gives us an epsilon dependence. And we have to take the partial derivative along q. We have to take the partial derivative along q prime, and this will give us two terms. And this introduces these two terms. And then we also have to use the chain rule to finally have this delta st. And yes, and this will give us the derivative along epsilon. And because epsilon is set to 0, all the higher order terms cancel. And for this last part, we use this trick, which is that we already took care of the border terms, so we can just put them into the integral without being bothered. And this is epsilon times a function of epsilon. So the derivative as epsilon goes to 0 is f0 plus 0 times f prime of 0. Of course, that is just f0. So we have the integral over time of delta sq dl dq plus delta sq dot dl dq dot. We put this all together, and we have this first term, then this second term, which has two parts, but they both look a lot alike. I factored it all along delta LQ and delta LQ dot, so that we could see it more easily. Then we integrate the second part of the integral by parts. So primitive this and derive this. Well, integrate this and derive this. This amounts to removing the dots because those are total derivatives, so it's all fine. We get this extra edge term, and here the edge terms are important because remember I said earlier, yeah, we start somewhere and we end somewhere, so it has to be to have this form. But here we're using the general shape of the action, and we don't really care about finding the trajectory. We care about the properties of the action. So our start and end terms do matter because we can take them to be whatever we like, basically. And through this, we find that this term has this in common and this in common. So here we have the equation of motion, I think, for delta x of the shape of this shape, and we know that this is 0 by Euler-Lagrange. So we can cancel out these two and only have this, which is the conserved quantity we were looking for. So for orbital mechanics, we have this Lagrangian, and we want to apply this. So our symmetries are either time translation, so delta st equals 1, delta sx equals 0, and so we have the energy, which is the gradient along v dot v minus L. So this gives us m over 2 v squared minus gmm over r, which is the energy that I used earlier. And now for conservation of angular momentum, we need to investigate rotations. Rotations are a bit more tricky because there's 3 of them, and they transform like matrices. So if you want to rotate a vector in 3D space, of course you're going to use a matrix. That's the normal way. Or you can use your imagination if you do it in your head, but doing it in calculations, you'll have to use matrices. We Taylor expand around small alpha, so we have the identity matrix, which is just denoted as 1. And then we have this intermediate matrix, which you can see is anti-symmetric. This is because the rotation matrices are orthogonal. If you have done a bit of linear algebra, this is very understandable. If you have not, it means that if you reverse this matrix, like if you take this term, put it here, take this term, put it here, you get the opposite matrix. So we will call this AX for anti-symmetric along the x-axis. So we have 1 minus 1 here. These are higher order terms, we don't care. And we have that delta Sx for rotation is always some anti-symmetric matrix times the x vector. The anti-symmetric matrix depends on the axis of rotation you choose. But if you have 2 axes of rotations, you should have invariance along all axes, I think, because there's only so much space in 3D space for rotation. Of course, if you go to 4D space, you can have 2 axes of rotation, but not have the full rotation symmetry. It's more complicated. But in 3D space, everything is nice. And so this gives us Li for the axis I is equal to the transpose of the momentum. Oh yeah, I say recall, but I didn't talk about it, so I'm going to do it now. Here, for our translations, you get the momentum, right? This will be clearer, I think. No, this will never be clearer. The definition of momentum is that it's the conserved quantity associated to translation. So if we go back here, you have this, and we don't have translation invariant, but if we had it, we would have the conserved. Well, momentum exists either way, just not conserved. So we have we just take the derivative along this, and we get mv. That's classic momentum. And so yeah, the conserved quantity along translations is always momentum by definition. So recall, this is momentum. Now that I said it, and we have for each axis of rotation that is that conserves the action, we have this form. So using the shape of our antisymmetric matrix, there's some algebra to be done, but you get this form. So p times cross x. This is the vector product, and I think it's also nice to see the cross product this way, because it shows you that cross products in fact correspond to antisymmetric matrices, right? It's not a real vector in 3D space. It doesn't transform like a vector would in 3D space under some transformation. Most notably, if you invert every basis vector of your space to have your new basis. So if your change of base matrix is -1, -1, -1, which is valid because it has a, well, on the diagonal, of course, which is valid because it has a determinant of -1, you don't get the same vector, you get the opposite vector. So it's an odd vector. Oh no, you get the same vector, you don't get the opposite vector. My bad, sorry about this. I got confused. So this means that pseudo vectors, hold on. Well, anyway, this means that pseudo vectors are in fact antisymmetric matrices. I don't quite remember how that transforms. I think you get the same vector, but I could be wrong. Yes, you get the same vector. Okay. This can all be summarized neatly if you are aware of Lie theory and stuff like that. But if you are aware of Lie theory, you already know everything I'm saying, so it's fine. By saying that rotations form a Lie group, so it's a symmetry, so it forms a group, and it's a continuous differential symmetry. So it's a Lie group, and we look for corresponding elements in the Lie algebra to find our little infinitesimals here, and to have our conserved quantity. Now, we would like to do the same for fields, because if you look at the other examples, so the couple pendulums, there's conservation of energy because time doesn't matter, but everything else matters because all the coordinates are angles, and of course there's a preferred direction, which is the vertical. So there's no conservation of momentum, there's no conservation of angular momentum. The only conserved quantity is energy, and I don't think it's very interesting to find the energy of the couple pendulum. So we go directly to fields, and here we use my favorite notation of all time, which is the little trick to include time in our vectors. So I'll denote something with an uppercase mu is a 4 vector. It can also be a 3 vector or a 2 vector, as long as one of the coordinates is time and everything else is space. I don't really care about which region of space you like the most. If you only like some planes better than other, then you can have 2D space and 1D time. But as long as there's some time, I'll use Greek indices. We can transform these coordinates as we did, but we can also transform the fields as we did, and that's something new. Sometimes they have like internal symmetries. If your field is not just this little phi, but it is a vector, you can rotate it. If your field is a complex number, which amounts to being a 2D vector, but you can rotate the complex number along its face, which is important for electromagnetism, but that's for another talk. And as always, the action is invariant under the transformation, so we just write it all out, like we did earlier. And we can get this this shape of the action. We do the same trick. We change our variables to get the minus here, the minus sign. I omitted the dependencies in most of the perturbation terms because they're always of order 2, of order epsilon squared, so order 2, and they won't matter in the end because we will apply the same trick. We have that phi x mu minus epsilon delta s x mu is equal to this. So I just Taylor expanded here. It's fine. And so we get this partial mu delta s x nu, which corresponds to taking the full terms like you usually do for deriving something, but each of these terms is all compacted into this Einstein summation notation. We can use this form now to get rid of the dependencies that we wrote, and this only depends on x mu and not anything else. And we get this nice big form that we can also then Taylor expand. And as always, we sacrifice all terms of order 2 or higher to the big O. And this gives us this nice shape. Now, we derive, we set epsilon to 0. As always, the border term will create this. So I didn't use the bracket notation because we're integrating over space-time, so it's more complicated. I don't have this start time and end time. Instead, what I did is I used this d mu delta x mu notation. So this basically means that you have a flux of something that is 0. You can Oh, hold on, it's a real good question. Aki Plazi 1124. So in the previous slide, is the second line obtained by an active transformation or a passive change of coordinate? Does Noether's theorem depend on this interpretation? So both, actually. You can, well, if you have an, let's say you have an electromagnetic field, right? So you can, through electromagnetism, change the phase of the electrons that go through it. That's one way to interpret it. Okay, it's a bit complex, but yeah. But if you don't really care about the electromagnetic interactions, so let's say you just have some magical way of changing the phase without affecting the dynamics, then you have an active transformation that doesn't change the action of your system, and so it doesn't change the physics, and so the quantities stay invariant. For just changes of coordinates, so just different ways to look at the same system, of course, everything works the same. Well, you can see this for changes of coordinates, pure changes of coordinates without involving any internal symmetries like phase for electrons, etc. You can see this in time translation. Basically, either for a time translation can either be you have your experiment and you start your chronometer at a different time, right? So you pick a different time to be now is the 0th second, and I'm counting from now. Or what you can do is just start your chronometer always at the same time. So we only have one timeline. So you start your chronometers at some time, but you do time translation by literally doing the experiment over and over again at different points in time. So the second example would be an active transformation because you are actively translating it in time by just doing it again. And or doing it later. Waiting is an active translation in time, for example. But the first one is a passive change of coordinates, and both are equivalent for this. There are specific cases where this difference matters, I think, because you introduce some. Hold on. It doesn't matter for conserved quantities, but if your quantity is not conserved, then you'll have some complications. And I think, yes, I think the difference, the important thing about this active transformation and passive change of coordinates thing, it becomes really interesting when you are thinking about relativity, right? Because, for example, if I'm looking at a car that's accelerating, either I look from the coordinates of the car or I look from the coordinates of the bystander on the road, but those are just passive changes of coordinates, and those are two settings where I'll get different equations to model my thing, because of course it's not the same frame of reference, etc. But if I have a gravitational pull on this car, so which I have, most cars operate inside a gravity sphere, except the one that was sent to space for $1 billion. Most cars, so this is physically equivalent to accelerating or decelerating your frame of reference. It is in the equations, but in the interpretation, it changes a lot because one is just a change of coordinate and the other is a real force. And when I heard sometimes online that Earth's gravity is due to the Earth accelerating towards us, this is bullshit. The Earth cannot accelerate to every direction. Well, it just doesn't make sense. You can think of it this way if it helps you sleep at night, but it's not a good interpretation of it. So yes, the interpretation of Noether's theorem doesn't change if it's an active or a passive transformation, but there are some physical systems for which this, especially in relativity, for which this distinction is very important. So thank you for your question. It was very nice. And where was I? I was there. So we derive this first term. We have the edge term that is here. So we integrate along the edge, and we use the Stokes theorem to have this form rather than care about the boundary of our region of spacetime, which we'll see afterwards is arbitrary, like we did earlier for the time in the classical Noether's theorem. And then we have also the terms that we have earlier with the hold on. No, there's no longer dependence. I already totally expanded everything. Okay, that's fine. We then have the same example that we had earlier, where this is just epsilon, this is epsilon, and we can just, this is linear in epsilon because I took out all the terms that aren't linear in epsilon inside this big O. So we directly have this. Sorry, I got a bit confused answering to the question and then getting back to the calculations. It's done explicitly in the paper anyway. So we have this in the end, yes, this in the big integral, and we do the same trick as before. It's always the same. We integrate by parts here, so we have this integral. By the way, this is why I could write this border term as this way. You know, it's basically the integration by parts trick. You have, it's equivalent, in fact. You have the integration by part here, so we have that this is equal to this minus this, because here the partial mu only acts on this term, and here it acts on all the thing. So if you just expand this using the product rule, yes, I think it has a name. It's like someone's identity. Anyway, you have the product rule. You will find that this that one of those terms cancels with this one, and the other one gives this one. So yes, that's why you can use this to write down the edge terms in your integrals. Or you could just say, oh, Stokes theorem, but that's not very explicit if you aren't aware what Stokes theorem is. Well, there's a talk about this. Yeah, you could always just read the paper about the musical isomorphism and generalized Stokes theorem. By the way. Anyway, I'm getting sidetracked. We have that by equations of motion, this specific thing is equal to this, and so this all cancels, these two cancel together, and we are left with this flux that is 0 along the integral. So this means that we have a conserved current, because we can take our region of spacetime to be any region we like, and so this equation, the d mu L delta Sx mu plus all this, is always true. So we have J mu, J mu is the conserved current. And this is the whole form for it. But we can do it slightly better, which is we don't touch our fields. We say the fields are, they are what they are. We don't really care about them anymore. Well, we do care, but we don't want to transform them. We only touch spacetime. So either we rotate or we translate or anything. And we can see that we can factor the delta S x into this expression. So there's a minus sign, but who cares? Where this is the energy momentum tensor, or stress energy tensor, I think you say in énergie impulsion in France, but you say stress energy. I'll say energy momentum. I can manage to remember to say stress energy every time. And this gives us the you can then factor this out. It's kind of hard to do if you aren't aware of the little trick of adding a delta in here, but if you have this trick, it's trivial. So, you have to have done some tensor calculus, like the bare minimum to have this trick. So it's not like hard. It's just you have to already have thought about tensors in your life. And let's take back our example field. So this is only 3-dimensional with 1 time dimension and 2 spatial dimension, because it's a surface that we had earlier. I didn't justify the terms, did I? This is the kinetic term, kinetic energy. This is the potential. And why do we have a gradient squared of the height of our waves, of our surface? We don't have to have waves. It's because you can imagine that if there's a height difference in the water surface, the water would flow towards one direction, so there would have to be something like a force, so there would have to be something like a potential. I basically just put in the terms that I needed to have my wave equation at the end, because I knew I just wanted waves. It's not a very physical model for anything, but I didn't want to start yapping about electromagnetism or quantum fields So I just put something that resembles waves on a water surface. It isn't a really good model. If you do the whole calculation, you get yeah, I know Aki Plazi. Yeah, I do a general relativity usually. Why are these two the same physical quantity, and when do they differ? They never differ. Actually, it's always the same. Here I use space, put translation, but this is not just a translation. For translation, the infinitesimal is the whole transformation, because it's linear, right? It's R. So if you have the real line, you take one little bit and you keep stretching it, you'll have the whole line. But in the transformation, the variation of the metric, what you will get, so what you said about the variation of the metric, what you will get in transforming spacetime is not just the real line. So the infinitesimal is just the tangent space around. It's getting very hard. Sorry, it's a deep question. The infinitesimal transformation is a basis vector of the tangent space at the origin, right? So you can't really say, oh, this is just a translation. No, this becomes a translation if the infinitesimal is all there is. But if you vary the metric, hold on. Can I get a whiteboard, please? I knew this was going to be useful at some point.
Yep. Let's open it up.
Hold on. This is very interesting. I'm getting sidetracked, but I love. I love.
I mean, it's
too much too.
Hey, it's your presentation. Hold on, let's switch to the other one. I've made one just for you. Top left corner, you have the 3 bars, 2 viewboards, and then over there, I think you can guess which one would be yours. I think this whiteboard may have just actually killed Rox's Discord. Whoops, stuck with a filler for now. Okay, technical difficulties. This sort of thing happens. Don't worry. I'll be honest, I am in no way, shape, or form capable of answering the questions, so unfortunately, we will need to wait for Ro to reconnect. But yeah, I myself also really appreciate the deep and interesting questions. Appreciate paying attention. I hope you are enjoying the lecture so far. With no issues whatsoever. All right. Okay, technical difficulties. This is all fine. Who is the other guy? Other than me? Are you asking who am I or who is Ro? Because also mispronouncing their name, so take a grain of salt. But that is the author of the paper. I hope you unless you mean me. Unless you mean me, because hi, I'm Make It. I don't really matter here. I am Make It, I don't really matter. The smart one. Right, so Ro, okay. That's who we're here to have to hold the presentation, because Ro written a paper right here. There we go. It is on the website if you would like to see. Written a paper called Theorist, Toolbox, and right, you have either access to the newest one or access to it more like broadly. And that is the paper about which this presentation is. Well, that's the paper that the presentation today is based on. Welcome back.
Can you hear me? And is
Yep.
my sound quality not too bad?
It's not bad at all. I take your Discord did
I switched
not.
to my second computer where I had chat, so I will need to
That's absolutely
do the
fine.
things. It's okay. Can you hear me?
Yes, perfectly fine.
Yes. Ha! Second computer trick. Poof. should be able to stream and get back to where I was. Where did I cut off? I didn't catch it. My computer crashed because in the explanation.
Yeah, before I think that was the fault of the whiteboard.
Yeah.
Still answering the question.
Okay, so I had some time to think about it. Right. So, if you transform your metric, you vary your metric, this amounts to varying your coordinates in a way, right? Because it means that your relationship between your coordinates, the way you use the space, changes. So, yes, this means that you will get some delta sx mu, and yes, and this delta sx mu is just the basis derivative of the thing you are deriving along. I'm sorry for the complications in the explanation. So it's not just a coincidence that the derivative of your Lagrangian, the variation of your Lagrangian along the metric is called the stress energy tensor, or the energy momentum, as I always say, but that's wrong, right? The stress energy tensor is the variation of your Lagrangian along the metric. It's in fact because of the conserved current thing. It's there's a deep link. I can't really expand on the full proof of why this is exactly the same quantity, but you can. I think you can like either find it in some textbook. I don't know if the ones I talk about in the ones on Zit library have it, but you can definitely find it in the textbook about quantum field theory and applications to quantum gravity. I think it's called this. I think it has the full proof of why this is the same. If it hasn't, then I'm sorry to disappoint you. But it's a good book. You can learn a lot about QFT using it, so it's fine. You won't have downloaded it for nothing. Okay, back to the example we talked about earlier. Always getting sidetracked by interesting questions. We have this form for the energy momentum tensor. What is stress energy? Sorry. What is important here to see is that you have this here and this here that look much the same. In fact, if you divide one, I think it's this one, by speed of light squared. No, it's this one. By speed of light squared, you get the other. And you can see that this is the case for the whole thing. It is always symmetric in its indices, and that's somewhat important. It is symmetric in its indices up to a sign. That's because I hid a lot of things under the rug in this presentation, and notably that we have to change the sign of the columns and the lines when using the metric. And in curved space, so this is only in flat space, but in curved space-time for general relativity, it gets much messier. So this is part of what I swept under the rug. But this is, in fact, symmetric-ish in the curved space-time way to see it. Well, also in the flat one. But if you do the special relativity treatment that this needs to have, you'll find that it has the right symmetries that you want. So it's always symmetric. We can interpret this. This is the energy. It's conserved quantity along time translation. So fine. These are I think this is the pressure. This is the energy density, by the way. This is the pressure. So it's the amount of energy that is transferred directly along the x-axis, and it's not energy. It's the amount of momentum transferred along the x-axis, and that has coordinate x. And these are shear energies. So these are the energies that have a specific spatial direction, but that propagate in the other one. And you can see that, of course, these are symmetrical because it has to be conserved in a way. And I think these ones are momentum. They should be, in fact. Yes. Now, final thing. You see there's not a lot of slides left, so I know some people will have difficulties understanding the whole field jargon right here, but and the whole talk about Lie algebras and stuff. But this is gonna get much simpler. We're gonna talk about Hamiltonians. So there was this guy called Hamilton, and he also somewhat invented analytical mechanics. I think the least action principle is sometimes called the Hamilton principle. But you'd think that for a guy who pinned down the action thing, he'd be all in on the Lagrangian. But apparently they decided to name the Hamiltonian after him. So I think he was more involved in this. And there's a very good reason for this. It's because he didn't want to have one second order equation like we had in our assumption 2. He wants to have 2 first order equations that we have here at the bottom of the screen. And so what he did to have these 2 first order equations was that he took the Lagrangian and he Legendre transformed it, which is explained in more depth in the paper, along the q dot axis. So the formula for this, so we set p, the momentum, to be dl dq dot. I think he just wanted to have something that depended on the momentum rather than the derivatives. He thought it was more physical something. He was right, in fact, but it works way better in quantum mechanics. There was something about Poisson brackets. Anyway, you'd have to ask him, but he's dead. So, to find the equations of motion from this, which is a well-motivated form, we trust the big guy Hamilton, is that you take the differential, or exterior derivative if you want to be fancy, and this is basically amounts to seeing in which directions h can vary. So it can vary along t, it can vary along q, and it can vary along p, because these are the 3 coordinates that it has, the 3 things it depends on. You'd think it depends on q dot, but it does not. Q dot here is something that has to be found as a function of p so that we can rewrite it all in terms of p. It's not very hard in most cases to find q dot in terms of p and just have h be a function of p and q. Usually it's rather simple. And you have also that, if you use this formula, you have also the differential for h is p dq dot q dot dp. Reading formulas aloud like this is a bit silly, but you can see it, right? Notably, there's this dt term, which we won't really care about, so we can ignore it. There's these 2 dq dot terms that cancel each other. So as you see, I wasn't lying. It really does not depend on q dot. There are extra. There would be an extra dimension that does nothing. And there's this dp term and this dq term. And here we can have that dl dq. We use the equation of motion, and that's just p dot, because it's d over dt of this, and that's just p dot by the convention we said at the beginning of the talk. And so we have this this formula for the exterior derivative. We identify q dot here to dh dp here, and p dot here to minus dh dq. And there we go. We have our Hamilton equation of motion. This is very useful if you are looking, for example, at the simple pendulum, for example, because you can then not really solve it analytically through this way, but you can draw the phase portrait of it. And this basically gives you what to expect of what will happen where, Because you can set up, you have a simple pendulum, so it only swings along one axis. And you draw a plane that has q as its horizontal coordinate and p as its vertical coordinate. And then you draw basically the fluid lines, so where it will go from one to another, which are the lines that the system will follow in this space. And through this, you can really get a good image of how this pendulum oscillates. It takes a bit of imagination when you just look at a phase portrait and then to say, oh yes, this means that a pendulum can do this and this and that. But it really shows you well the use of phase portraits. I think they use way more in engineering, or they were used at some point, because I remember they were mandatory in engineer formations earlier in France. My physics teacher used to tell me about this. Anyway, now I'm sorry for everyone who hated the part about fields and thought it was impossible to understand, but I'm back on my field bullshit. We'll do the same thing for fields, and this time we have to break the holy grail of relativity. Hamiltonians are in fact not covariant at all. I already hear you guys booing. Even if you don't know what covariant means, you should be booing, because it's very bad. Because we install time as a privileged quantity, and it doesn't deserve it. It's just like space, you guys. And so I'll denote pi to be the derivative of the Lagrangian along the time derivative of phi. And we have the same formula, h equals pi dt phi minus L. So these are Lagrangian densities and Hamiltonian densities, but the subtlety always escapes at the moment you start talking about fields. You just say the Lagrangian, because the density word is basically, we're talking about a field, it has to be a density, it's redundant. We do the same thing. So we differentiate this formula. You can already imagine what this will give us. Here, so these two terms we don't touch, this term we don't touch. We have to split this tensor term because, again, we are booing, time is privileged. And so this term first. There's an extra line here that's a bug. Hold on, I should have reread this. Ignore this line. This term here, we use the equations of motion on it. And we can find that. Hold on, what did I do? Sorry. Okay, I got it. This term here cancels with this term here. Yes, as I did earlier. So I should have found it directly. So this is just me rewriting this, but I forgot this partial thing. So there should be this right here. And so we can regroup this. We can use the equation of motion. No, that's not it. Oh, this is integration by parts. Yes, this is the density. So it sits inside a volume, so we can integrate by parts. And we get this. It's much clearer in the paper. And we... Yes, we get this minus sign here. And we can then fully use the equations of motion. Finally, I was itching to do it for the whole time. And get partial t pi. And this is what we wanted, because we can just compare here and get the same, we can just identify and get the same equations. So, quick look if there's a question. Yes. I'm aware that my name is unpronounceable if you don't know French, but because I saw people talking about my name in the chat. Or my pseudonym. My actual name is also unpronounceable if you don't know French.
Well, it could also just be me. Other people...
No. English speakers routinely have trouble with it. As a summary, go read the paper. As you saw, I kind of had trouble justifying the last thing. I think it's an integration by part. I'd have to look back at it, but I was perturbed by all the perturbations in the metric and stuff like that we're talking about. Analytical mechanics is a very powerful tool that is used everywhere in theoretical physics. It pops up really, really everywhere, and if you are not talking about Lagrangians all day long, you aren't really doing fundamental theoretical physics. You are still doing something that looks like physics, most likely, else you wouldn't be listening to this long-ass talk. But considering Lagrangians all day is really most of the job for a big part of the theoretical physics community. Also, as you saw, there's a lot of calculations, and I didn't pick the examples that I think are the most calculations intense. I think the most intense thing in the paper is the exercise with the hanging cord, because it's just eons long afterwards to find the actual shape after finding the equations of motion. But it's chill. It's a nice thing to do during the summer. You can just say, oh, today I'll calculate this or whatever, and it just gives you some time. You could also try if you feel like, I already know about analytical mechanics, I know how to integrate fields and stuff like that. You can try to prove actually, I think I'm gonna do it afterwards, like on my own, but not on stream. You can try to prove the thing about if you have a Lagrangian that depends on the metric. This is Chinese for most people. It's the functional derivative of the Lagrangian along the metric. So that's 2 tensor is the energy momentum tensor as we defined it. You can do it for a Lagrangian that has one field and the metric as its secondary field, but of course the metric shouldn't really be involved in the field part. Well, in the metric shouldn't be counted as a field of matter, rather. So yeah, thank you for your attention. I hope you had a nice time. If you want to really dig deep in this, I think most physics undergrad need to have a class, or most physics undergrad programs have a class about analytical mechanics. I think else it's just a nightmare to learn it on your own because it's a very deep subject. It's a lot of ground to cover. I think my paper is good as like an introduction to it or as a cheat sheet, but it doesn't replace a textbook. It doesn't replace a class. And having an actual professor who has like more experience in the field, who uses it more than I do, or is just more experienced in physics, is a big plus. So definitely don't skip classes, you guys. Go see your professors. Go see your how do you call the people who give the exercise sessions? Tutors, whatever. Teaching assistants, your TAs. Go talk to them. This is also the way to get a PhD if you want to stay in the same place or to get a network. So really, if professors know your face, that's the one way to get ahead because they know who you are. Well, I had a blind professor once, so they have to also know your voice, I guess. But if they know one of the two, that's already a big step. And yeah, that's how I think you can get the most out of this because talking to people is directly face to face is always more instructive and always a lot more efficient than just trying to do stuff on your own, trying to find the answers to questions online, etc. So yeah, thank you for attention. This was all. I'm gonna keep this on if there's any closing questions. Do I recommend any books for self-study? I recommend any book because so if I saw you talking about metric and stuff, so I think you specifically should be rather interested in. I'm gonna give you the reference. I should have it. Yeah, it's the book. Hold on, I'm gonna type it in the chat. So it's called Introduction. It's available online through Zlib. I don't tell YouTube I said it online, but you can get books. I said it in here, but you can get books for free. So it's Introduction to Quantum Mechanics, Quantum Field Theory with applications to quantum gravity. Okay, this one is I recommend it because you asked questions earlier that I think are answered in the book. I'm not quite sure, but anyway, I think it's quite the things you want to look at if you're already talking about the stuff you were talking to me about. It's by Buchbinder, which is a funny name if you know what it means. Shapiro, and only these two. And you can find it on the library, which I think you need an account nowadays to download books from. This one. It starts off very nice with some very understandable things. Like the first chapter is the second chapter is about relativistic symmetry. Then it talks about field models and Lagrange formalization. And very quickly it becomes the absolute nightmare of renormalization, which like as I said, I didn't quite manage to study renormalization using the book. I think I'm gonna really need the class to understand it. But the first few chapters are really understandable. If you really want to learn analytical mechanics the other way, so I'm only going to talk about what is findable in the library because that's where I get my book. So you just type analytical mechanics in the search bar, and you don't take the original one by Lagrange, which is the fourth result usually. This one is like eons old at this point. Anything by Cambridge University Press or Oxford University Press is usually really good. Try to pick the most recent one. So this would be the one. Yes, I think this one is good. I can directly tell you it's Analytical Mechanics by Lemos. I checked these earlier, but it may not be as good as I remember. I don't think this one has exercise in it. It should have, but I don't remember. You cannot read it all for free online. Okay. Just download it, I think. Yeah. I'll download it and I'll be able to send it to you if you join the Discord or whatever, if you really want it. Yeah, it has everything. Up. It has problems too, so that's really nice. I don't think it has solutions to the problem. But anyway, it has everything you want in there, the basics. It has it's Cambridge University Press, so always good place to find books. And also it's available for free if you are not shy about doing a little bit of piracy. Which it isn't, you know, it shouldn't be paid. I don't think the author gets that much money from it anyway, which tends to be the thing with publishing. Yeah, it has everything. It goes in a lot more detail than I do in the paper, and if you really, really want to study it for real, it has to be the thing. There's even, I'm looking at a paragraph called Variational Principle, Physics and Metaphysics. This may be going a bit too far, guys. If you're considering metaphysics, you may want to switch to philosophy department, but anyway, it's very I think they put it in there as a joke. It has everything. It talks about orthogonal. It explains everything you want. Small oscillation theory, yes, Hamiltonian dynamics, of course. Does it talk about phase? Does it show a phase portrait? Okay, I'm looking through it right now as I talk, so this may not be the best thing. So definitely, I recommend picking the second thing I typed out in the. I think I just doxed myself using my real account. It's fine. I think it's fine. It's fine. Everybody knows who I am. All right. Well, Black's already knew. You should pick up the first one as an undergrad and the second one if you're a grad student. So the first one is a nice overview of analytical mechanics. The second one goes really in deep on fundamental physics. If you want to study more quantum physics, you're not really interested. The Koen-Tanuji, I think I wrote it correctly, is always good. You just type this in any search bar of any website that has books, well, science books. You will find it. It's everywhere, and it's really, really, really the best quantum physics book out there. It's written by people. I don't quite remember. I think they all three got a Nobel Prize for working on cold atoms, right? So these guys really know what quantum physics is about. Okay. And so yeah, could you repeat the order? I'm not in school, by the way. Okay, that's fine. You can learn anything anywhere. It's I would recommend going 2, 3, 1. Because the first one is the one I use, which is why I thought about it immediately. But it's also not very accessible, I think. Okay. But of course, don't only take my advice, because I only I'm only talking about the ones I used, and I don't have an overview of everything that is online, like and every book ever written. I forgot Griffith, of course. Griffith's books. So if you have a subject that you think is grad or undergrad level, anything by this guy, I think I wrote it correctly, I hope so, else it's quite unfindable. Anything by this guy is usually very good.
I mean, Griffiths is the Griffiths. Like, I have no knowledge of relativity whatsoever, and even with that, I still know, for example, Einstein's notation is the basics of special relativity because of Griffiths.
Yeah.
Effectively. So
it's the one thing his full name is David Jeffrey Griffith, apparently. It's really the thing you want to be reading if you Introduction to Electrodynamics, very known. It's mostly used by Americans in France. I learned about it when I think from Angela Collier, which is a big inspiration for me. It's very nice. It's the classic, like, you know. Oh, if you want to self-study it, while I'm here talking about Angela Collier, hold on. Let's go to her channel. She has a full-on video about what you should do if you want to self-study physics. So I'm just gonna link you to her channel, because
if you're gonna send a link on YouTube, YouTube has a tendency to eat links if they're sent. I'm just gonna type the self-study. Okay, good, because it does it in a very dirty way where it still shows it to you but doesn't show it to anyone else.
Yeah, I'm gonna send you the title of the video. It's this one: How to Teach Yourself Physics. by that's her ad on this website.
Actually, hold on. I'm pretty certain I can give you moderator, and then you should be able to send them.
Well, anyway, this is the video you want to look at because she, of course, has a much better depth of knowledge than I have, being like older and also having actually used most of the books she talks about. And I think she was a TA or a professor at some point, so I think definitely TA. So she has had to give out these recommendations. It's really good. She has a really good channel where nowadays she mostly talks about like her gripes with life and the state of the world. But she also has really good videos that do sort of science communication. She always says she isn't a science communicator, but anyway. And yeah. Oh, I'm stand-on moderator. Okay. So I will try and send you a link. Like, if you don't see it, it's fine. Just type the name of the video in the YouTube search bar. You should find it. Yeah. Things to avoid are Instagram accounts and random, like, if someone promises you quantum healing or something, run away as fast as possible, because I know a lot of people I know there's some people who fall into these kind of traps. Well, they are, oh, I'm excited to learn physics, I want to learn about quantum mechanics, and then they go full on conspiracy theorists, like I don't quite remember the one about they suppressed the 216 hertz length wave or whatever. Like, don't do this. Be serious. Only use like real textbooks, and don't go on random websites where they make stuff up, and there are mostly bots that just like will put anything on the internet just for fun. So yeah.
And that is why you should go to sliceofpie.eu and look at the library.
Yeah, exactly. Really good thing. That's something where we actually read the papers, we verify them, we check that everything is that everything is fine. Like, this is a good channel. Make it as a good channel.
There we go.
We actually do science and not just conspiracy theories. That's already a big plus compared to half of the internet, more than half.
So yeah, and I will also at the end. I don't know, by the way, if you still want to keep going with this, because I don't want to kind of cut you short. If you...
No, it's fine. I'm done.
Right.
I've said everything I wanted to say.
That's good, because I do have to say you are really good at presenting. You are public speaking, and it's honestly I am impressed.
It is. I won French debate. I already doxed myself. Like I think you can see my name from the account. Yeah, you can see my real name, so I can just say it. I won a French debating tournament. I'm really good at talking in public. I'm not as good as talking behind a camera. Like this isn't my prime, but yeah, it's something I do.
I can see that. Yeah.
Also in France, we have more education about presenting stuff, as I think Reblax can confirm. We have a lot of, let's say, presentations that can go either way.
Well, I'm glad to have had you here. Unfortunately, I will also need to go because this has been a bit planned a bit late, which is a shame, to be honest. I really am looking forward to more. I don't want to like push you or peer pressure you into doing it. But
I'll definitely write a thing about covariance. I already know.
Because
covariance is too important to not leave something online about it. And I had a lot of fun writing the paper. I tend to get bored when I have nothing to do, and so this summer break is perfect time to write some more.
I am really gonna be looking forward to them, and I'm really excited for the next presentation. All right, and I think for now it's gonna be it. As always, once again, the links are right there in the chat to go to the library, but if not, then sliceofpie.eu, and then the library button is right there. The papers are available there, but there are also more papers that you could check out, be it by Silver, be it by Joel, be it by even Remco, Ash. There are plenty different fields. Based on this, most likely would imagine everyone here is interested in physics, and there are a couple of physics ones that you